So in this session, we're going to finish off this topic that we started on inductance. So I'll pick up where we left off last week. So one of the things we looked at last week was the oscillations in an LC circuit, or in a capacitor inductor circuit. So these are really important circuits because they oscillate, and we went through how they oscillate. So I'll go over again briefly how these circuits actually can oscillate. So if we imagine here we've got a capacitor and an inductor that are connected to each other, and we're going to start off by charging up the capacitor to introduce some energy into the system. So we start off with a charged up capacitor, and then we can then flip this switch, and then that connects up the circuit. And so because we've got a charge on one side of this capacitor, then that's going to start flowing through the circuit. So this current from the capacitor is going to start flowing along here and through the inductor, and that current will increase, and then it will reach some maximum, and once it's reached a maximum, then the magnetic field in the inductor will be at a maximum, and then as it starts to decrease, so as this charge becomes depleted and it starts to decrease, then because of the way an inductor works, in that it will try and keep any current going in the direction that it was going, so as it starts to fall off, then the inductor will try and keep the current flowing in the initial direction as the current from the capacitor decreases. So once we've exhausted the supply of charge from the capacitor, then the magnetic field in the inductor will then start to push the current around in the same direction and start charging up the opposite plate of the capacitor. So we then end up with a situation where the magnetic field then is decreased down to 0 in the inductor, and all the current has now charged up the opposite plate of the capacitor. And then the opposite happens. So then that charged up plate will then start to discharge, and we'll get current flowing back in the opposite direction. And again, as that current increases, we'll build up a magnetic field in the inductor. And then once we reach a maximum current, which then starts to decrease from this capacitor, then the inductor will try and keep the current flowing in the same direction. And then we come back to the position we were to start with this plate charged up. So this oscillation that we get in LC circuits just comes from the properties of capacitors and inductors. So we can't get an oscillating circuit just built of capacitors, and similarly we can't get an oscillating circuit that's just built of inductors. Like, we need to connect a capacitor and an inductor up together to get this oscillating circuit. And it's from the fact that a capacitor will tend to push back any charge that it's got stored on it, and a inductor will try and keep any current flowing that's sent flowing through it. So it's from these properties that means that when you connect the capacitor and an inductor up, they will oscillate back and forth. So then I introduced then some the research that I'm looking at that's related to this. So I showed you a superconducting LC circuit. So this is just some recent research I've been looking at, where we've got a capacitive element and an inductive element that are patterned onto a kind of chip. So it's just some superconducting metal patterned on top of a crystal there, and then this operates at microwave frequencies as an LC circuit. So let's look in more detail then at an LC circuit. So let's imagine then we've got our capacitor and inductor connected up in a circuit, and again, to analyze what's going on, we can come back to Kirchhoff's loop rule. So we used this in the first semester to look at circuit networks, so networks of resistors and voltage sources. We looked at it to derive this part of the equation for the voltage of an inductor when it's in a circuit with a resistor and a battery. But we can do the same when we've got a capacitor and an inductor in a circuit. So we can choose a loop, so we can any direction is okay for analyzing using Kirchhoff's loop rule. So if we follow the direction of travel of this loop that we've drawn in the LC circuit, then if we go round the loop and then we get to the inductor, so we've got some current going in this direction, and then we know that the voltage on the inductor will try and oppose that, so we'll have some positive voltage here, so we're going to step down, so that will be some negative voltage there, and then on this capacitor we've got a positive charge here, so we're stepping down in voltage, so we've got a minus sign here, and then we know the voltage on a capacitor from C equals Q over V, so the voltage on that capacitor will be charge over capacitance, and then the voltage on the inductor will be the inductance L multiplied by the rate of change of current, di dt. But since we know current is the rate of change of charge, so it's a flow rate of charge, so at any instant the current is dq dt, so how quickly that charge is changing with time, its flow rate, then we can say di dt is the second differential of charge and time, so d2q by dt squared. And then we can substitute this into our equation above and then divide by L. Let's get this L out here, and then we can get a nice differential equation here. So we've got d2q by dt squared plus this constant here, this 1 over LC, so this circuit parameter that comes out. So it's just the two things that we can change in our circuit, the capacitance and the inductance, and then that's multiplied by Q, and then we know that equals 0. And then if you look at this equation, then if you've looked at simple harmonic motion before, then this should remind you of the equation for simple harmonic motion. So if you've got a pendulum or a spring that's oscillating, and then you've got some displacement x and some spring constant k and some mass m, then the equation that describes that motion is the same form. You've got d2x by dt squared, that's the acceleration, and then you've got this system parameter, the k over m, the spring constant divided by the mass, multiplied by the displacement, and that equals 0. So you can see there's this nice analogy between these two systems, the LC circuit and the mass spring system. And it's a very good analogy to make between an LC circuit and a mass spring system, and the equations show that. So in an LC circuit, the capacitor charge Q plays the role of the displacement X. So if we look at what is analogous to what, so you can see in our equation here, here's the charge on the capacitor, here and here, and you can see the analogous quantity in the mass spring system is the displacement X. And then the current, which is the rate of change of charge, is analogous to a particle's velocity in the mass spring system. So velocity is rate of change of displacement, and current is rate of change of charge. And then the inductance L is analogous to the mass. So we've already kind of made this analogy that an inductor works like something with inertia. So we can describe it really well as something with inertia, something that wants to keep going in the same direction that it's being pushed, but will initially resist being pushed. And then the reciprocal of the capacitance, so 1 over C, is analogous to the force constant you have for a spring, K. So you can see we've got K here, and then that's equivalent to 1 over C here. And then for a harmonic oscillator, so if you remember from what we looked at, what you've looked at before for harmonic oscillators, where you've got a mass spring system, then the frequency that it oscillates at, omega, which is 2 pi times the frequency, so this is the frequency in radians, which is 2 pi times f, the frequency in cycles per second, and that is dependent on the spring constant and the mass, and it's root k over m. And then the position as a function of time just follows cosine function so we've got some amplitude A here, that's time. So we just get this cosine wave that describes the oscillation. And then analogously, the charge on the capacitor and the current through the circuit are also functions of time. So the charge on the capacitor will oscillate, and again, some cosine function with some particular frequency and then some phase difference. And then we take the differential of that for current, and again we get the same waveform, but it's just displaced, so the sine is going to displace it by 90 degrees. And then, because we then we get this omega come out over here as well. And so in an LC circuit, the angular frequency, omega, is root 1 over LC. So if we've got an LC circuit, we know the value of the inductance and the capacitance, then we can calculate the frequency, this angular frequency, that it will oscillate using this equation. So we just plug our numbers for L and C into this equation, and we'll get out an angular frequency. as long as we've got SI units for L and C, so then that's going to give us our angular frequency. So we can collect then all the different equations for a mass spring system and an inductor capacitor circuit, and then compare them side by side. So if we've got our mass spring system, then as a mass spring system is oscillating, then we're continuously exchanging between kinetic and potential energy, and the kinetic energy is half mv squared. And then similarly for the LC circuit, we're exchanging between magnetic energy stored in the inductor and electrical energy stored in the capacitor. So the magnetic energy in the inductor is half Li squared, and then the potential energy in the mass spring system is half kx squared, and then because K is equivalent to 1 over C, then the electrical energy in the LC circuit is Q squared over 2C. And then if we get the total energy of the system, so that the potential energy plus the kinetic energy, which is the total energy of the system, where A is the amplitude of the oscillation. And then similarly for the LC circuit, we've got the magnetic potential energy plus the electrical energy in the capacitor, and that is equal to the total energy in the system, where Q is the total charge that we've got in our LC system. And then we've got equivalent equations for the velocity and the current, and then we know that velocity is rate of change of displacement and current is rate of change of charge. And then the angular frequencies that these oscillate at, we've got omega is root k over m, and then for the LC circuit we've got omega is root 1 over LC. And then both of them have some similar cosine waveform that describes their motion over time. So you can see that both analytically, looking at the equations, we've got a nice analogy, and just thinking conceptually about how these two different systems work, there's a nice analogy between a mass spring system and an inductor capacitor circuit. So let's have a go at a question then. So remembering these equations, so particularly this one for an LC circuit, omega equals root 1 over LC. So we've got our LC circuit, we've got an inductor L and a capacitor, capacitance C, are connected as shown. And if the values of both L and C are doubled, what happens to the time required for the capacitor to charge to oscillate through a complete cycle? So if we double both the value of C and the value of L in this circuit, what's going to happen between the time between cycles? Is it going to be A, it becomes 4 times longer, B, it becomes twice as long, C, it's unchanged, D, it becomes half as long, or E, it becomes 1/4 as long? So you go to the polev.com/markh website. So I will activate that question. Okay, so that's activated, so have a go at that. I'll write the equation down here that we looked at the last slide. Okay, we've got 2 responses so far. Yeah, we've got 4 responses now. Okay, we've got 5 responses, give it another minute or so. Okay, so go over this one then. So far we've got 2 people have gone for B, it becomes twice as long, and 3 have gone for D, it becomes half as long. So let's go through this. So we're going to say both L and C are doubled. So if we double L and C, then this bit, that's going to be that's going to be a quarter of what it was originally. And then when we square root that, it's going to be half. So the frequency is now half. So we've got half the frequency, but the question is saying what happens to the time between the cycles? So the frequency is halved. We've got some particular frequency, and then and then that frequency is halved, the time between the cycles doubles. So we're looking for B. The time between the cycles becomes twice as long. Okay. So let's have a look at some of the applications of LC circuits then. So like I said, that the LC circuits are really important circuits, so they've got lots of applications in signal processing and communication systems. So you find them, for example, in tuning radio transmitters and receivers. So when you're tuning a radio to a particular station, the LC circuits are set at resonances for that particular carrier frequency. So when you're tuning any circuit, you've got an LC circuit. When tuning radio, you've got some LC circuit that is changing its frequency to whatever frequency you need to pick up. They're also used in amplifiers and oscillators, so in filters. So you often need circuits that can filter out certain frequencies, and in mixers as well, and also contactless cards where you've got RFID, so they use some LC circuit in order to oscillate at the right frequency. Let's focus on LC circuits in radios. So this is the first type of radio that was ever made. So the very first radios that you could get were known as crystal radio sets, and the simplest form of crystal radio set you can get has just 3 components. So here on the left you've got the circuit diagram for them, and all you need in a crystal radio set is an inductor, a capacitor. So here we've got a variable capacitor, so, and a rectifier. So in this case it's a diode. So with just these 3 components alone, you can receive a radio signal. So this symbol here is for an earphone. So that's just something that can make a sound. It's not a speaker. It's something that has to go in your ear. So you'll notice in this circuit there's no battery, right? So there's no active power source. So all the power that's driving the circuit comes from the antenna, right? So you've got a tiny amount of power in the circuit, but human ears are really sensitive. So if you send this into an earphone, your ears can actually pick up the sound that's being powered by just the antenna. So here on the right we've got some examples of different crystal radio sets. So the LC circuit here we've got here, that's the part that tunes the radio. So this radio needs to oscillate at a particular frequency. So that frequency needs to be the frequency of the radio station you're trying to pick up. And so if you're tuning this to tune through different radio stations, you need to vary the frequency of the LC circuit. So you can either do that by varying the capacitance. So in this circuit diagram, we've got a variable capacitor here, so that arrow through the capacitor symbol means you've got a variable capacitor. And see on the bottom here, so this picture of a real crystal radio set, down here is a variable capacitor. So it's just some plates that you can rotate and slide over each other. As you rotate them around, you're changing how much those plates overlap, and so you're changing the capacitance. In this one on the top, I think it looks like it's got a variable inductor. So it looks like you move this connector up and down so that you're connecting different parts of that wire that make up the inductor. That's what it looks like to me, because I can't see a variable capacitor in there, but you can do either. It's a bit more difficult to make a variable inductor than a variable capacitor, but either varying the capacitance or the inductance will change the resonant frequency of the LC circuit and change the frequency of the station that it picks up. And then the final component is the rectifier, so something that allows current to only flow in one direction. And in the original crystal radio sets, you had a crystal here, which is what gave them its name. What this actually is a Schottky diode. So when these were originally made, like well over 100 years ago, the makers didn't really understand what they had or how it worked. They just knew that this crystal could rectify. All it was a crystal that behaved as a semiconductor, although I don't think they really understood what semiconductors were at the time. And then, difficult to see here, but you've got a tiny wire that's known as a cat's whisker. So what you had was some semiconductor material here, and then there was some very thin wire that contacted on the surface. And it's that contact between a metal and a semiconductor which creates what's known as a Schottky barrier. And that barrier is rectifying, so it allows current through in one direction or the other. And because it's a surface effect, it's very dependent on exactly how that wire contacts on the surface of the crystal, the semiconductor. And so you can see here there's actually some adjustment. You got something where you can play around with how that wire contacts the surface. So with these crystal radio sets, you could vary either the capacitance or the inductance to change the resonant frequency, or you might need to change this little cat's whisker, this wire that's contacting the surface of your semiconducting crystal to make sure that your rectifier is working properly. But the way this circuit works is you've got your antenna, and what that's picking up, if we were to visualize the signal that's coming in, the radio frequency that's going in, you'd have some amplitude modulation, so you'd have some relatively low frequency of the signal you're trying to send, so that could be someone speaking, which has got relatively low frequencies in it. And then you'd have this being carried by some radio frequency. So you've got some radio frequency that's oscillating very quickly. So if we looked at the radio signal, then we'd see, this is time. Then this would be the important component, is the electric field component. So the electric field, and then once that's picked up by the antenna, then in the circuit, this electric field will be converted to a voltage. So the voltage in the circuit will be doing this, And so the reason that we need this rectifier in there is because we've got this high frequency oscillating voltage, but you can see it's oscillating around 0, so the average voltage that we'd get would be 0. So we have the LC circuit to tune any particular frequency because the antenna is picking up a whole load of different frequencies. So this LC circuit will then only oscillate at the particular frequency that you want to pick up, and then this rectifier will only allow current in one direction. So what you'll get then after the rectifier is current only doing this. So now the voltage is no longer averaging at 0. So what we've actually got is the actual voltage. So I'll draw that again. So the actual voltage that we get after the rectifier, it's going up and down at different amplitudes depending on what the signal is that it's carrying, say a human voice. So we've got a whole load of peaks in voltage, so it's peaking very rapidly in time, but overall it's averaging to some particular signal, so say the sound wave that you want to pick up in the earpiece. So this isn't actually ideal, but it works. So you've still got these high frequency peaks in voltage that are being sent to the earphone, but the earphone isn't usually going to pick that up because it's trying to make the earphone move too quickly. So even with this simple circuit, you'll just end up with the overall envelope of that signal, which is the sound wave that you want to pick up. You can actually put in a smoothing capacitor here, so you can put in a capacitor here to smooth out these peaks in voltage that you're still getting from the radio wave carrier signal, but you don't actually need that. So if you think about it, it's kind of incredible that you can build a radio circuit with just 3 components. Remember when I was a kid, I did actually build one of these. I had a little electronics kit, so there's a little thing with some electronic components, and you could connect them up with wires, and there's some different projects you could do. And one of these radios, these passive radios, is one of the projects. It's one of the simplest ones you can do. You've just got 3 components to connect up. I remember I don't think I ever picked up any recognizable sound. I definitely did hear some sounds coming out an earphone. I tried tuning it, the radio, quite a lot. I don't think I ever picked up a radio station, but the issue is the antenna. So if you're using one of these passive systems which is powered by the antenna, essentially you do need a pretty big antenna to pick up enough signal power to power your earphone. So let's have a go at another question then. So we've got a radio tuning circuit, and the minimum capacitance of the variable capacitor in that circuit is 4.31 picofarads. So what is the inductance of a coil connected to this capacitor if the oscillation frequency of the LC circuit is 1530 kilohertz, corresponding to one end of the AM radio broadcast band, when the capacitor is set to its minimum capacitance. So we've got a capacitor set to this capacitance, and we want to get this frequency out. So what is the inductance that we need? So I'll just give you the equation again. We've got our omega equals root 1 over LC. So I think to remember, this equation is for angular frequency. That's just 2 pi times the frequency. So the frequency of radio stations isn't given in angular frequency, it's just in hertz, in cycles per second. So have a go at that at this part A, and then I will activate this on pole everywhere. Okay, well actually let's take 10 minutes break there. So let's take a 10-minute break, and you can think about this question in the break if you want, and then I'll activate the pole everywhere question in 10 minutes. So I'll see you back here in 10 minutes. Okay, let's make a start. So, um, have a go at this question, this part A, if you haven't already. Um, so I've activated the poll everywhere site. So it's an open response, so you can type in your answer. So once you've got your answer for the inductance, just type that in to the poll everywhere site. Okay, first one in. You're way too small there. Um, hmm, make Yeah, if you get that so small, make sure you've got the right units. So you know what a picofarad is. Right, so picofarad is 10 to the minus 12 farads. Make sure you got those units right. Last one in. Um, yeah, that's spot on. Well done. Yeah, last one in. Well done. That's right. Yeah, last one in. Well done. That's spot on. Okay, let's give it another few minutes and then we'll go over the answer to this one. Okay, part B in yeah, whoever sent part B in, you're right for part B. Okay, so we go at the answer for part A then. So start off our equation. So omega equals, so that's a typo, that should be up there. So it's root 1 over LC, and you know that omega is the angular frequency, so it's 2 pi times the frequency. So if we rearrange this to get L, so square both sides, multiply by C, and then take the reciprocal, then we'll get this equation. And we plug our numbers in for the frequency and the capacitance, and then you should get 2.62 times 10 to the minus 3 henries. Okay, let's have a go at part B then. If we look at part B, then saying the frequency at the other end of the broadcast band is 545 kilohertz. So what is the maximum capacitance of the capacitor if the oscillation frequency is adjustable over the range of the broadcast band? So let's have a go at part B now. Okay, so I've activated the file everywhere site, so it's an open question. You can type in the value of that capacitance. So here from the first part we got 2.62 times 10 to the minus 3 Henrys. Okay, last two answers in, that's spot on, well done. Okay, let's give that another few minutes and then we'll go over the answer to part B. Okay, let's look at part B then. So we rearrange the equation again, but instead we just rearrange it for capacitance. And so the maximum capacitance corresponds to the minimum frequency. So we just take that equation, as before, plug in our frequency, plug in our value for the inductor, and then that gives us 32.5 picofarads. Okay, so let's look at now LRC circuits. So we've looked at LC circuits, so circuits with a capacitor and an inductor in, but any real circuit will have some resistance in it. So components, the wires, so the inductor and the capacitor will have some certain resistance. And so even if we don't want an LRC circuit, we actually have some form of LRC circuit. So if we consider this circuit on the right, so we can initially charge up our capacitor and then flip this switch over so that it can discharge into the circuit. So, like we said, any real circuit will have some resistance in, or we can introduce our own resistance into the circuit as a resistor. So having this resistor in the circuit will change how the circuit behaves. So if we look at the oscillation of an LRC circuit over time, then we're going to have that circuit oscillating at a particular frequency, but over time the magnitude of those oscillations will decrease over time. And that's because the resistor is damping the circuit, so it's absorbing some of the energy each time the current goes back and forth over the resistor. We're getting I squared R losses, so it's going to, some of that power will be dissipated in the resistor, and so we'll gradually lose energy in the circuit, and the oscillations will gradually damp out to zero. We also change the frequency slightly. As long as we're not purposely introducing resistance into the LC circuit, then the kind of stray resistance that we've got, the unintended resistance, won't have a big effect. But the equation for the frequency of an LRC circuit has this extra term in it. So we've got this extra term that's got resistance in it. And then as we increase the resistance, we're going to start reducing the frequency. And eventually, once this term, this R squared over 4L squared, once that equals 1 over LC, then you can see this frequency will come out at 0. And that's what we call a critically damped system. So the resistance is damping the oscillations, and once we get to a particular resistance, so the resistance where these two terms are equal, then we have no oscillations at all, and the circuit would just do this. It would just come down. The charge would just reach 0, and we wouldn't have any oscillations at all. So that is actually the end of this topic. So I'm going to finish slightly earlier than normal. So have a good Easter break. I'll see you back after the Easter break. I'd recommend doing some revision during the Easter break, and particularly don't forget to revise what we did in the first semester. So the exam that you have in May, that will contain material from the first semester as well. So I'd advise revising the first semester, particularly the January test that you did would be ideal. And I'd also advise looking at the more analytical problems that we've gone over in this semester for revision. So when we don't have COVID regulations and the online tests, you'll notice I often include some of the more conceptual type questions in the exam questions, but because of the way we've got to assess this year, I'd look back at the conceptual questions so that you get a better understanding of the concepts, but the examination will need to be focused more on the analytical questions that you've looked at. Another thing to note is that what we've done in this semester is different from any of the other semesters. So I've taken over this semester from previous lecturers, so the material is different to what we've looked at before. There may be some similarities, similar topics, but it might not be so useful to look at previous exam questions for what's done in this semester. For last semester's stuff, then it should be fairly similar going back a few years. But other than that, I will hang on for a few minutes here if there's any questions, but I'll see you after the Easter break. So have a good Easter break.